Good. Okay, how do we predict data using the RBF? Then, just as a reminder, so predicting data or simulating the network on new data, we need to have the set of centers. We need to have the transfer function phi. We need to have the weights and biases W and B. Okay, and so now we're going to assume that W is M by K and B is M by 1. Okay, and so now what we want to do is we have new data, new input data. Let's just call it X, and X is going to be, let's say, N by, should we use N by P? Sure, what the heck. Good. And so what we want to do in this section is we want to construct the output Y, which will be M by P. Okay? It's pretty straightforward. We basically do what we did before. Number one, whoops, sorry about that. One, compute the distance matrix. And so we'll assume that that is, do you remember how big that's going to be? K by P, right? This is number of centers by number of input data. So typically, right, this would be a wide matrix. That's K by P. Okay. 2. Compute the design matrix capital phi by taking phi of the phi of D. Okay. 3. Once we get that, then Y is equal to W times phi plus B. Done. There you go. All right. So that is the prediction for you. Good. All right. So going along with the notes in the handout, the example that I show you there is using this exponential function, and the thing to get out of the example in the book is that the number of centers can change, can affect the error, right? So we have a curve that looks like this, and so we would want to use like this, the minimum value here, whatever the number of centers is right there. How big is that on this graph? It's about 7. And this is the error. This is the number of centers. And so using a graph like this, you could find, this is the error on the test set, by the way. You could figure out how many centers would be optimal for your problem. Okay, so that's a nice thing to keep in mind. By the way, if this was not the test set, if this was the training set, what would this graph look like? It would look like, whoops, we wouldn't have a negative number, but it would look like that. Because the training is going to go to, the error on the training set is going to go to 0. Good. In the exercises, we show where MATLAB got their square root of minus natural log of 1/2. And so that's always good. So that's a good problem to look at. I may assign that for you. It doesn't take too long, and I think it's good practice to see where that came from.